Now, you might recall that the first derivative tells you if a function is increasing, or decreasing. So that's what the first derivative tells us. Okay? If f prime of x, increasing or decreasing, if f prime of x is greater than 0, that essentially tells us that our slope is greater than 0. So our function is going to be increasing. While if f prime of x, your derivative, is less than 0, that means your function has essentially a negative slope, right? So your function is going to be decreasing. Okay? Now, in this video, we're going to explore the second derivative. So if I take the derivative 2 times, what is that going to tell me? So the second derivative tells us if our graph is going to be concave up at certain intervals. So concave up kind of just looks like a smile. So like if I were to pull up Desmos right over here, if I have the function, let's say f of x is equal to x to the second power, notice how this is like a smile, right? It's going to be like curving upwards, right? Notice how like the slope is constantly increasing, right? So when your kind of graph looks like a sort of smile, that is when your graph is concave up. You can think about the endpoints as sort of pointing up in this case. While a graph is concave down, when you have a graph that's concave down, well, just think about a frown, right? If I place a negative x squared here, this looks like a frown, right? Our graph is going to be concave down, right? The slope of the line, right? The slopes, that's going to be constantly sort of decreasing, right? The slope is constantly decreasing. And you guys might be wondering a little bit, this is really confusing. So for the second derivative right over here, you're essentially taking the slope of my slope. And yeah, that's essentially what we're doing, right? Once again, a graph that is concave up, right? If we have a graph that's concave up, right? This is going to be the graph of y is equal to, or f of x is equal to x squared. When your second derivative, when your second derivative is positive, that tells me that the graph is concave up. All right. Now, why does that sort of make sense? Well, think about it, right? The first derivative, f prime of x, tells us if our function is increasing or decreasing. So right now, right, if I take a look at y f of x is equal to x squared, notice how at, let's say, this point right over here, our function is decreasing, right? The slope of the tangent line is negative. However, notice how as I keep going along this curve, our slope is going to be increasing, right? The slope of my tangent line is going to be, it's going to keep on increasing, right? It's going to keep on increasing. So f prime of x tells me that the slope of my slope, essentially how fast is my sort of slope changing. Notice how as I move from one x value to the next x value, notice how the graph gets steeper and steeper, right? My slope is getting more and more positive, right? My slope originally was very negative, then it becomes more and more and more and more positive, right? And if slope is becoming more and more and more positive, well, then it's going to form a smiley sort of face, right? Your slope is just going to become more and more and more positive. So that is what I mean by when a function is concave up. All right, the second derivative of your function is less than 0. What that tells me is that, well, our function is going to be concave down. Notice how for the graph of y is equal to negative x squared, well, notice how the second derivative tells us how fast is our slope changing, right? How fast is our slope changing, the slope of the slope. So notice how as my x value increases, look what happens to my slope. My slope starts out positive, right? Super positive, then it gets less positive, then it becomes more negative. So when our second derivative is negative, that tells me that my slope is getting more and more and more negative as my x value moves on. All right. So we're not just looking at the slope of the line; we're looking at how the slope changes as the x value changes. So that now, when our second derivative is equal to 0, that can tell us a couple of things. I mean, the first thing it kind of tells us is that at the point where our x value makes this equal to 0, at that specific point, right, our graph is neither concave up nor concave down. So for example, if I have a function that looks something like this, right, notice how at this point right over here, notice how my function f of x, it's neither concave up nor concave down, right? So um, that would be something, that would be a situation where second derivative is equal to 0. Now this actually has a specific name. This is something known as an inflection point. This tells me that the concavity of our function is changing at this point. So, for example, I mean, sort of around this point. So, if I were to take a look at this graph, notice how as I go up towards this point, notice how the slope of my line, is constantly decreasing, right? Originally, we had a very positive slope, then our line started to get less steep, and then now we have a very little slope, right? So from, let's say, this point to kind of negative infinity, it looks like, right? It looks like that my function is going to be concave down. However, after I pass this point, then my function starts to become concave up, right? Then our function starts to be concave up because our slope is starting to increase, right? The slope of my slope is starting to increase, right? Slope is constantly increasing now. So from this point right over here, not including the point, all the way up to infinity, well, our function is concave up now. So notice how I'm changing from concave down to concave up, right? So an inflection point basically tells you that the concavity of my function is changing. All right, that's what an inflection point tells me. All right, before the inflection point, it's some sort of concavity. After an inflection point, the concavity changes. It doesn't always have to be concave down to concave up. It could be concave up, switching to concave down. Either way, the inflection point tells us the concavity is changing around this point. But there's also another scenario. If your second derivative is equal to 0, that can also just tell us that our function is sort of like a straight line. Because think about it, right? Let's say if you have the function f of x is equal to 9x, for example. If you take the first derivative, you get f prime of x is equal to 9. And if you take the second derivative, you get f double prime of x is equal to 0, right? So now, no matter which x value you put in, this f double prime of x is going to be equal to 0, right? And now, if I were to graph f of x is equal to 9x here, right? If I were to graph f of x is equal to 9x, which y is equal to 9x, notice how this function is neither concave up nor concave down, right? It's just a straight line. There's no concavity changes, nothing, right? When you set the second derivative equal to 0, well, sometimes there's no concavity at all, right? So there's not going to be a concavity change. The last scenario for the second derivative, let's just say if we have f of x is equal to x to the fourth power, take the first derivative, we get 4x to the third power. And if we take the second one, right, just do the power rule again, and we get 12x squared. Now, we are going to set the second derivative equal to 0. So I'm going to set 12x squared equal to 0, right? I set this equal to 0, and notice how when x is equal to 0, right, when I plug in 0 in for x, my second derivative is equal to 0, right? So at x is equal to 0, this is a potential inflection point, right? A sort of point where the concavity of the function changes. However, there's a problem, right? If we look at f of x is equal to x to the fourth power, notice how our concavity doesn't change at all, right? X to the fourth power, right? It's always going to be concave up. So once again, this is sort of a third scenario, right? This is a third scenario. When you set your second derivative equal to 0, right, it can give you one of the sort of three information, right? It can either be that at this specific point, there's an inflection point. It can tell you that your function is a completely straight line, but it can also tell you that, this is just sort of a point where the concavity does not change. All right, so when you set your second derivative equal to 0, at this specific point right over here, the concavity doesn't have to change, right? It can remain sort of the same. So for, x to the fourth power, the second derivative is 0, right? Our second derivative is equal to 0 when our x value is equal to 0, right? So we set those two things equal to 0, right? But the thing is that our concavity stays the same at both sides. So this would not be an inflection point. Now, I did all of the first derivative work, and I found out that for the function f of x is equal to x to the third power, my function from x is equal to from negative infinity to 0, right? Not including 0, but I found out from this interval right over here that my function is going to be increasing. And I also found out that from 0 to infinity, not including 0, my function is also going to be increasing. And this is how you kind of apply the first derivative, right? Hopefully y'all have learned how to apply the first derivative in terms of sort of critical points, right? Something when you set the first derivative is equal to 0, find out if the function is increasing or decreasing at certain intervals. In the second derivative, it's a very similar process, all right? So the second derivative of x to the third power, well, if we know the first derivative is 3x to the second power, well, our second derivative, that's just going to be equal to 6x, right? That's just going to be equal to 6x, doing the power rule for this, right? Now, what we're going to do, first of all, is we're going to find out possible inflection points. Remember, inflection points? Now, if you want to find potential inflection points for your function, remember, you have to set your second derivative is equal to 0. So that's exactly what I'm going to do. I'm going to set my function, the second derivative for my function, I'm going to set that equal to 0. So 6x is equal to 0, and therefore x is equal to 0. So this tells me that at x is equal to 0, there's a possible inflection point for our function x to the third power. Now, how do we check if it's actually an inflection point and not just a trick, right? Because remember, if your second derivative is equal to 0, that's not always guaranteed that's an inflection point. And the way you check if it's an inflection point or not is you're going to use this number line thing that is very similar to what you've been doing when you've used the first derivative for your critical points. So you know that x is equal to 0. Let's just put it right over here, and we're going to test x values in these different regions of the number line. So notice how when I draw this x is equal to 0 right over here, it splits the number line into two sections, right? I'm going to test the value from this section. I'm going to test the value from this section, and let's see if it's an inflection point. So let's say if I choose x is equal to -1 right over here, right? So I'm going at this part of the number line first. Well, my x value is -1, right? So when my x value is -1, notice how my second derivative is equal to -6, right? So when x value is -1, second derivative is equal to -6. Notice how our second derivative is negative. And I said how when your second derivative is negative, your function is concave down, right? Your function is concave down because the slope of your line is just going to be constantly sort of decreasing, right? The slope of the slope is going to be getting more and more sort of negative as x value increases. So I'm going to say from when your values are from -infinity to 0, not including 0, well, that's going to tell me that our function is concave down. So it's going to be concave down. Okay. So if you test one value from this region and it works, that basically tells you that all values from this region works. Okay. So that means all values between 0 and -infinity, that's all going to be concave down. Now let's test the value from this region. Let's say if I plug in +1 here. If I plug in +1 for my second derivative, I plug in +1 here, I get 6 times +1, which is just +6. Remember, when your second derivative is positive, that tells me that my function is concave up, right? The slope of my tangent line is just going to be constantly increasing as my x value goes on. So that means from 0 to infinity right over here, not including 0 because, well, 0 is our potential inflection point, right? There is no concavity for that point. So that means from this region right over here, 0 to infinity, our function is going to be concave up. Remember what the definition of an inflection point is. It's a point on the graph where our second derivative is equal to 0 and our concavity changes, right? In this case, notice how from -infinity to 0, our concavity is we're concave down. Notice how as we pass the 0 and go to the positive region, our graph is concave up. So there is a change in concavity, and that tells me that this is an actual inflection point. This isn't just a trick, okay? So you're going to do, when you're doing these second derivative problems, you're kind of just seeing this, you're doing this number line trick, right? Setting it equal to 0 to find potential inflection points. You're going to test the values below and above this inflection point to see if there's a change in concavity, all right? And, these answers make sense because, look, this isn't a complicated function. This is f of x is equal to x to the third power, for God's sake, right? So you guys probably know what f of x is equal to x to the third power looks like. It looks something like this, right? Notice how from -infinity all the way up to 0, notice our function is concave down, right? The slope of my tangent line is just going to be constantly decreasing, right? It's getting less and less and less steep. However, from 0 to infinity, not including 0, notice how the slope of my tangent line is constantly increasing, so we're concave up. So, these answers make sense, right? They line up with how the graph actually looks like. Now, let me ask you this question. If a function is increasing, does that mean that you're going to be concave up? Concave up, right? Does that mean you're going to be concave up? That is the question. And the answer to this is No, your function doesn't have to be concave up if the function is increasing. In fact, the first derivative things and second derivative things are kind of independent from each other. All right, they're completely separate things. All right, let me give you an example. So a simple example of this would just be if you have x squared, f of x is equal to x squared. Notice how the function here is decreasing, right? From negative infinity to 0, our function is decreasing. It's still concave up. Here, from 0 to infinity, our function is increasing, right? It's still concave up, right? So kind of the concavity things, all of that, they're independent from each other. So just because a function is increasing doesn't mean that it has to be, concave up, or it doesn't have to be, concave down. You actually have to check that manually. All right, I really like this problem. Determine which values are inflection points and which are not. And a hard follow-up for this is try to sketch out what this function looks like, without using a graphing calculator, just from your kind of knowledge of first derivative groups. All right, let's begin. Let's start out with A. So remember, inflection points, all of that, you're going to be dealing with the second derivative, right? So first derivative, if you do the power rule on this, you're just going to get 4x to the third power minus 6x to the second power. If you do it another time, you're going to get 12x to the second power minus 12x. Okay? Now, remember, to find inflection points, what you do with the second derivative is you set this equal to 0. So 12x squared minus 12x, you set this equal to 0. How do we do this now? So to find out the values of x that make this equal to 0, the first thing I notice is that there's a 12x squared and 12x right here. So I can factor, right? I can factor out a 12x from both terms, and I get x minus 1, and then this is going to be equal to 0. So at x is equal to 0, right? Either x is equal to 0 or x is equal to 1, and these are our potential inflection points. All right, so at x is equal to 0, x is equal to 1, those are our potential inflection points. Now to actually check if they are inflection points or if they're just a fake, I'm going to do the number line trick. This side represents negative infinity. We're going to draw 0 here. Now we're going to draw 1. And then this side is infinity, right? This is from 1 to infinity, right? Now, let's see. Let's say we pick out a number from this region. And also, once again, notice how this divides up the number line into 3 parts. We test the number from each part of this number line to see if it's concave up or concave down. So look, let's say if I plug in -1. So if I plug in -1 into this, actually it might be easier if we plug in -1 into our factored thing. So let's say if I plug in -1 into this right over here, I'm going to get 12 multiplied by -1, and then this is going to be multiplied by -1 minus 1, so -2. So 12 times -1 is going to be -12, and then negative makes a positive, right? So notice how when our second derivative is, when we plug in -1 for it, notice how this is going to be greater than 0, right? It's a positive value, meaning that from essentially negative infinity to 0, right, basically encompassing this entire region right over here, right, that includes -1, we are going to be concave up. All right, concave up. Now, let's try out a value from in between 0 and 1. Let's say if I plug in 0.5, so 0.5 or 1/2. All right. So when I plug in 0.5 here, I get 12 times 0.5, and that's going to be multiplied by 0.5 minus 1. 12 times 0.5 gives me a positive value. 0.5 minus 1 gives me a negative value. A positive value multiplied by a negative value makes this entire thing negative. So when I plug in the value from second derivative of 0.5, right, notice how this gives me a negative value. And this means that we are going to be concave down, right? So we're going to be concave down. The way I like to remember this is, if your second derivative is greater than 0, it's going to be concave up. You can think about being greater than 0 as being greater, kind of up on the number line, if you will, right? If you're concave up, second derivative is going to be greater than 0 because a positive value is up on the number line, while a negative value is down on the number line, so you're going to be concave down. Now we can try a value that's greater than 1. So let's say if I plug in 2. So notice how when I plug in 2 into my second derivative, the factored version of the second derivative, you could also plug it in here, but it's just simpler to look at it in its factored form. right? When I plug in 2 here, I'm going to get 12 times 2 multiplied by 2 minus 1. I know it's a positive value multiplied by a positive value. So therefore, when we plug in second derivative is equal to 2, that's going to give me a positive value. So that means this whole region right over here, because our second derivative is greater than 0, that's going to mean this is going to be concave up. Okay? So what are our potential inflection points? Now remember, inflection points occur when our concavity is changing. So notice how at x is equal to 0, the function changes from concave up to concave down. That's a concavity change. So at x is equal to 0, there is an inflection point there. What about x is equal to 1? Well, notice how at x is equal to 1, we change from concave down to concave up. So at x is equal to 1, that's also an inflection point. So boom, that's number 1. All right, now we have to take a look at our first derivative, and we have to find critical points. Remember, critical points are found when you set your first derivative equal to 0. Factor out, what can we factor out? We can factor out a 2x squared from both terms. It's going to be 2x, right? And it's going to be minus 3. It's going to be equal to 0. So our potential critical points are going to be when x is equal to 0 and when x is equal to 3 over 2, right? Now, once again, we're going to test out if these points actually work. So we're going to do the same number line trick we did, right? 0, this is 3 over 2. Now, at x is equal to 0, right? Well, notice how when we draw x is equal to 0, x is equal to 3 over 2 on this number line, right? It splits the number line once again into 3 parts. We're going to test the value from each part and see if our function is increasing or if it's decreasing and all of that, right? To see if we have maximum points or if we're dealing with minimum points, right? All of that. And you'll see how all that plays in when we actually graph the function. So anyways, if I plug in -1 here, right, I'm going to use this factored form of my first derivative. All right, I'm going to use the factored form of this. Notice how when I plug in -1 here, I get 2 times -1 to the second power. So that's +1. And then this right over here is multiplied by -1 multiplied by 2 is -2 minus 3. So essentially what we have here is a positive value being multiplied by a negative value. That's going to give me a negative value, right? Right, that's going to give me a negative value. Now recall that when your first derivative is less than 0, remember, the first derivative, that's just the slope, right? So if your slope is less than 0, that means that your function is going to be decreasing. All right, so when I'm dealing with concave up to concave down signs, sort of the second derivative things, when I draw out the number line, sometimes it might be good to just sketch concave up, concave down, concave up once again, right? But when you're dealing with increasing or decreasing, I like to just draw the arrows, right? It's just a simple representation of what's going on. Anyways, let's plug a value in between 0 and 3 over 2. Let's just say 1, right? 1 is the same thing as 2 over 2, so I know that's in between these two values. When I plug in 1 into here, I get 2 times 1, which is just 2, and then 1 squared is the same thing as 1, and I'm going to multiply this by 2 times 1, which is just 2. 2 minus 3 is just a negative number. A positive number multiplied by a negative number, once again, that's going to be decreasing, right? So our function is just going to keep on decreasing. Now let's see what happens if we plug in a number that's greater than 3 over 2. Let's just say, I don't know, 2, right? 2 is the same thing as 4 over 2, so I know that's greater than 3 over 2. Anyways, plug in 2 here, I get 2 multiplied by 2 squared, which is just 4. That's going to be multiplied by 2 times 2, which is 4 minus 3. Notice how we have a positive value multiplied by a positive value. And that means that we're going to get a positive value. That means when we plug 2 into our derivative right over here, right, it's going to be greater than 0. If your slope is greater than 0, you're going to be increasing, right? So that means that this is going to tell me about whether a point is a minimum or maximum. Notice how at the point 0 right over here, right, this is not a minimum, nor is it a maximum, right? Because at x is equal to 0 right over here, all we're given is that from negative infinity, we're given that from negative infinity to 0 right over here, our function is decreasing, right? And then we're given from 0 to 3 over 2, our function is still going to be decreasing, right? So at x is equal to 0, this is not a maximum point. This is not even a minimum point, right? If you have a line here, if a function is decreasing, let's say if it's something like this, and 0 is kind of just like in the middle of all this, it's neither a maximum nor is it a minimum, right? It's just going to be like in the middle, right? It's not really, it's neither. So we're going to ignore this 0. Now, if we look at 3 over 2, well, this is interesting because look, notice how from x is equal to 0 to 3 over 2, we're going down, right? Our function is decreasing. But then we go back up. So look, think about it. If we're going down and then we go back up, what do we have here? We have a minimum point, right? So, at x is equal to 3 over 2, that is our minimum point. And this also makes sense why we have a minimum point, because remember, we're dealing with a function. Our original function was an x to the fourth power as our sort of leading our leading exponent, right? X to the fourth power is our leading sort of, our leading power, right? It's the highest power in our function. And you know how x to the fourth power looks like, right? It looks just like a parabola. This parabola has minimum point. So, all of this stuff, matches up. All right, and one last thing I'm gonna do is I'm actually gonna go to my original function right over here, and I'm actually gonna find out. So it runs to them. I'm actually gonna find out what values make the original function equal to 0. So yeah, when you do these types of problems, you kind of have to set everything equal to 0. The first, second, and even the original function equal to 0. So when I set this equal to 0, I can factor out an x to the third power term. And notice how when our x value is equal to 0 and when my x value is equal to 2, those are my zeros for my function. I have all the ingredients for my recipe. Let's get started. We're going to graph this, right? Now let's graph the obvious first. We know that at x is equal to 0 and x is equal to 2, those are my zeros for the function. So those are the zeros for my function. Now I know from, now let's take a look at my, actually, let's take a look at the first derivative, actually. All right, so I know that at x is equal to 3 over 2, that's going to be a minimum point. So at x is equal to 3 over 2, that's going to be a minimum point. So I'm just going to draw a very low point. That's going to be my minimum value. If you actually wanted to find out the y value for this minimum value, you could just substitute 3 over 2 into the original function, and you would get the value. Anyways, now after we found out our minimum values, right, after you kind of plotted your minimum, your maximum values, now it's time to look at your second derivative. So yeah, first step, you do the zeros. Second step, you plot the minimum and the maximums. And third step, you look at the second derivatives. All right, second derivatives, this tells me that from negative infinity to 0, my function is going to be concave up, right? So it's going to be concave up. Notice how my slope is constantly increasing, right? It's going to be like a U shape. Now from 0 to 1, so this is saying that from 0 to 1, my function is going to be concave down, right? So from 0 to 1, my function is going to be concave down. And then it says that from 1 now to infinity, my function is going to switch to concave up again. So this is going to be an inflection point, right? This is going to be an inflection point, and now my concavity is going to change. My concavity is going to change. We're going to reach my minimum point, right? Using the first derivative, I said how my minimum point was at 3 over 2, so I'm going to reach my minimum point, and then I rise up back again, right? Because I'm concave up. And guess what? I'm concave up until infinity, right? I'm going to keep going up. So this is how our function is actually going to look like. And guess what? If you want to check your work, even again, if you're not so sure about how your work is doing, once again, you can look at your first derivative. So kind of the last step here is to confirm everything with your first derivative. First derivative tells me that from negative infinity to 0, my function is going to be decreasing. Is it decreasing from negative infinity to 0? Yes, it is. What about from 0 to 3 over 2? Is it decreasing? Oh, yeah, that's definitely decreasing. And guess what? What about from 3 over 2 to infinity, right? From the first derivative, we said how from 3 over 2, we also said how from 3 over 2 to infinity, our function is going to be increasing, right? And look here, from 3 over 2 to infinity, our function is increasing. So everything lines up, and there we go. This, if you went on Desmos and you cheated a little bit, I don't blame you. This is a pretty hard problem, but yeah, if you actually wanted to get the specific values for everything, just plug it into the original function. But if you know how to use a graphing calculator or just a normal calculator in general, then that shouldn't be too much of a problem. And yeah, that's pretty much how you use the first and second derivative and apply it.